Hello and welcome to our demo video. The purpose of this video is to demonstrate our Capstone project that we created as part of the Aggregate Intellect workshop to build and deploy natural language processing models. We will be demonstrating how we applied machine learning, NLP concepts, and DevOps techniques to create a fully deployed user-facing application. This was a team project, and the members of our team included Het Barrett, Krista Banati, myself, Ali El-Sharif, and Mahmoud Artima. We chose a text classification problem, taking in a question as input, then using machine learning methods to determine if the question belongs to one of 6 predefined classes. This is a well-defined problem, and there is a wide body of literature illustrating various techniques to solve it. Note that text classification has theoretical and practical significance. It is the first step in achieving high performance in answering questions. We can also think of a number of real-world applications in which classifying questions would be useful. For example, think of a call center where questions would need to be routed to a specialized agent depending on the area of expertise, sales, technical support, etc. The diagram on this slide shows the general outline of a machine learning text classification problem. The diagram illustrates text classification being broken down into a training phase and a prediction phase. During the training phase, the raw text is fed into a feature extractor that converts the text into numeric features that can be processed by a machine learning algorithm. In our case, we used CountVectorizer, bag of words, to obtain a matrix containing a count of words from the vocabulary. The matrix was then used to get the term frequency multiplied by the inverse document frequency to obtain a weighted representation of each term's importance in the vocabulary. The machine learning algorithm, in this case it was a support vector machine that we used, takes the extracted features and generates a classifier model. During prediction time, the same feature extractor is used to convert new unseen text into the input features that the classifier will understand and generate a prediction label. The data in this particular example, and this particular project, was sourced from PyTorch, and it's a benchmark data set that's pretty widely researched and cited, and it has 6,000 labeled examples. Each one of these labeled examples belongs to one of these 6 classes: entities, locations, numeric values, human, description and abstract concepts, and abbreviations. And just to get you an idea of what that data set looks like, here's a sample question: who was the inventor of silly putty? And this is labeled as a question about a human. A couple of things to note about this particular data set. You would note that with the exception of abbreviation, this is a balanced data set. There's no one class that significantly is overrepresented in the data set, and the only underrepresented class is abbreviations. We did a lexical dispersion plot, generated that from the data set, and noted the word what was evenly distributed across. Some of these words, you can see how they would be associated with a particular question type. For instance, who would be associated with questions related to humans, and where would be generally associated with questions related to location. And though that lexical dispersion plots is good to just visualize the associations with these classes. There were a lot of tools that were used in developing, modeling, packaging, and deploying the solution. We included we used the Python NLTK kit, as well as the Google SciKit Learn. We used the Colab as a development environment, which basically had a Jupyter notebook that was stored in a Google Drive. We used MLflow for model pipeline and for packaging models. And we used Dockers as a container for the model, and Flask for model inference. GitHub we used as our basically code repository. A couple of things of note in terms of the results. The accuracy metrics for the model that we developed were quite high. This is a small data set, so I would not read too much into it, but for the data set that we had and the testing metrics look pretty good. I mean, you can see here on the ROC curve, for each of the individual classes, the curve is reaching out to the upper left corner, and that's as near perfect as you can get. The individual accuracy metrics, precision, recall, F1 score, are plotted for individual classes, and this column over here illustrates the number of instances that were used in this testing. And again, the sample size is fairly small with 500 test instances. There is definitely room for improvement, and I would not expect this level of accuracy out there in the field, but this is a fairly good result based on the size of the sample that we had. We went a step further and validated the model through generating a model explainer. And what you would see here is the utilization of a package called LIME, which stands for Local Interpretable Model Explanation. And this is a model agnostic post hoc method that treats the explainer or the classifier as a black box, generates an explanation for an instance based on statistically sampling around a decision boundary for a particular example, and attempts to identify the key features that determined the classification for that example. And in this particular case, we fed it where in the world is Toronto, Canada. I'm really lost and I can't find it. And you would note that it predicted with 100% probability that this was a question about a location. And it gave us the feature contributions that contributed to that classification. Where is contributed to heavily, and world and find were second and third. The the text, the surrounding text, in which these features, key features that would help determine the classification, are also highlighted, and this just gives us an additional level of assurance that this is not a classifier that was trading to noise, and it actually used logical words to arrive at the decision or the classification that it made. Next, and following this conceptual video, you'll be seeing a video about demonstrating the application that we created.
Welcome to the Capstone project for Team 3. First things first, I'm going to quickly walk you through our code, high level. We used the PyFunk model wrapper in order to save our model. As you can see here, we're passing the input through a CountVectorizer, which tokenizes it, converts it into a bag of words, and TD-IDF, and then we're using an SVM classifier. We are saving our model with Pickle as well as a label encoder, which we are passing as our artifacts, and those artifacts are loaded into our context in our MLflow wrapper, and we're saving that here. Next, we created a Flask app, and in this Flask app, we are loading in our model from MLflow, PyFunk, and we are letting the user pass a question, and we then return a response, and we return a response in a human readable way. We then used Docker to containerize our model, and I will now show you that everything is working. So I'm going to run our Flask API through Docker here. and we're going to go to port 5001. And here's our website. So let's demonstrate that this does in fact work. Who is the Prime Minister? Submit. Human being, well done, correct classification. How old is my father? Submit numeric values, correct. Where are my socks? Location, excellent. Thank you for watching our demo.